These are the video notes for Module 8, an Introduction to Probability. We will be looking exclusively at probability throughout the remainder of Unit 2. So the first thing we need to establish is rules for probability. There are two rules that we're going to need to remember for the rest of the semester. The first rule is that a probability is always between 0 and 1. We can also write this as P of an event X is less than or equal to 1 and greater than or equal to 0. If you have a probability of 0, that means the event is impossible. For example, it is impossible to roll a 7 if you roll a single dice. So what that means is the probability of rolling a 7 is equal to 0. Meanwhile, a probability of 1 means it is certain to happen. So the probability of rolling a number between 1 and 6 is 1. Okay, you are definitely going to get a number between 1 and 6 when you roll a single dice. The second rule to probability is that the sum of all probabilities, that's not an S, the sum of all probabilities is equal to 1. So if I look at the probability of rolling a dice and I look at the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6, I add all of those probabilities up, it will equal 1. So those are the two most important rules to probability that we're going to need to remember for this semester. So now for the remainder of these notes, we're going to look at two ways to assign probability. The first is the classical method. This is where you use counting techniques to determine probabilities. So to look at this, we're going to look at an example where you're playing Monopoly. So Monopoly is a board game. You roll 2 dice, and then that allows you to move your token. So in this game, you have landed in jail, and you need to get doubles in order to get out of jail. So we're going to calculate the probability that you get out of jail or you get doubles on your very next roll. So what I've set up here for you guys is a table of values. The top row of numbers here, this represents the value of the first die. And then this first column here, this represents the value of the second die that you roll. So what we're going to do is we're going to list out all the different combinations that we can get when we roll 2 die. So for example, we could roll a 1 and a 1. We could roll a 2 and a 1, a 3 and a 1, a 4 and a 1, a 5 and a 1, or a 6 and a 1. Then we roll a 1 and a 2, a 2 and a 2, a 3 and a 2, 4, 2, 5, 2, and 6, 2. Then we have a 1 and a 3, a 2 and a 3, a 3 and a 3, 4, 3, 5, 3, 6, 3. So we're just going to keep doing this for all of our numbers. Okay, so the first number I'm listing out is the value for the first die, and then the second number is what we got on the second die. Okay, and this just makes it a little bit easier to be able to see all of the ways that I could roll 2 die. Almost done. I'm going to go ahead and do these two columns together. All right, so there's my completed table of all of the different ways that I can roll 2 die. So what we need to know is what the probability is that I roll doubles. So what I want to do is I want to look at all my combinations and I want to find the ones that contain doubles. So that's where the first die and the second die are the same number. So we have a 1 and a 1, 2 and a 2, 3, 3, 4, 4, 5, 5, and 6 with a 6. So those are all of the ways that I see that I could roll a double. Okay, I'm not actually rolling the die right now. I'm just looking at what I could get, what could happen when I roll these die. So what is the probability that I roll doubles? Well, the first thing I want to find is how many ways could I have rolled doubles. So there are 1, 2, 3, 4, 5, 6 ways that I could roll doubles. So the probability of doubles equals 6 divided by, and then how many total possibilities are there for rolling 2 die? So how many combinations do I have? So if I count up all of these combinations, I find that there are 36 possible combinations. So this top number 6 was the number of ways that I could roll doubles, and then I'm going to divide that by the number of total combinations. And then we always want to turn our probabilities into decimals. And we get 0.1667. In this section, I've been pretty lenient as far as giving me 4 decimals in the past. In all of Unit 2 and Unit 3, if you do not give me 4 decimals, so 4 numbers after the decimal point, I will start taking away points. This is where it becomes very important for you to give me 4 decimal points, and always give me 4 decimal points. Okay, so now we did it, we got out of jail. So we want to buy a property that is 8 spaces away. So we need to find now the probability that we land on the space that is 8 spaces away on this turn. So I'm going to come back up to all of my different combinations, and now I want to find all of the ones where if I add the dice numbers together, I get 8. So for example, this first one, 2 and 6, I can add those together and it gives me 8. 3 and 5, 4 and 4, 5 and 3, 6 and 2. Those all give me a sum of 8, which is what I need because the space is 8 spaces away. So now I have 1, 2, 3, 4, 5 ways that I could roll an 8. So the probability of an 8 is equal to 5 over the 36 possible ways of rolling the dice. So I do 5 over 36, and that gives me as a decimal 0.1389. Okay, if you did 36 divided by 5, let's say you switch those around, you get 7.2. And you can come back up to this first rule and see that a probability has to be between 0 and 1. So that says, okay, maybe I messed up. Maybe it should actually be 5 over 36. So if you ever calculate a probability and you get a number that's bigger than 1, or you get a negative number, go back and look and say, okay, did I flip-flop the division, or did I count something wrong? Okay, those are ways that you can check to make sure when you're doing this that you're doing everything correctly. So this is the classical method. So it's just looking at counting how many ways can I get this. So I counted how many ways I could roll 2 die, and then from there I counted how many ways could I get doubles and how many ways could I get an 8. So now what we're going to look at is the relative frequency, or the empirical method for calculating probability. So this is where you calculate probability by conducting an experiment or by collecting information. So it's not something that we're going to count, we're actually going to perform the experiment. Okay, so we're looking at the Monopoly example still. We're not going to look at doubles this time, we're just going to look at the probability that I land on the space that I want, which is 8 spaces away. So what I've already gone ahead and done is I've rolled 2 die 20 times. And I put a tally mark next to the number that represents the sum. So for example, the die roll where they summed together and it was a 2, so I got a 1 and a 1, that happened 2 times. The sum of the die equaling 3, that happened 2 times, and so on and so on, and I kept doing that until I got to 20. So now what we're going to do is we're going to calculate the probability of each of these die rolls based on the experiment that I've conducted. And what I'm going to do is I'm going to find the probability by taking the number of times I saw that event and dividing it by the total number of times I ran the experiment, which was 20. So 2 over 20, and that's 0.1. And then I have again, 2 over 20, 0.1. This one is 1, 2, 3, 4, 5 over 20, which I believe is 0.25, but I'm going to double check that. If you aren't sure, just double check it anyways. Yep, 0.25. 2 over 20, which is 0.1. 4 over 20, 0.2. 4 over 20 again was 0.2. 1 over 20 is 0.05. And then 9, 10, 11, and 12, I didn't see any of those. And that's just from my actual experiment. If you were to go and do this, you may see rolls of 9, 10, 11, and 12. I just didn't happen to see it when I did this. So these probabilities all sum or are all equal to 0. Okay, so based on my experiment, the probability that I saw 9, it didn't happen. So it's equal to 0. So this should look very familiar to you because we've actually already looked at calculating probability in this method. We just didn't call it a probability yet. Remember way back in the beginning, Module 4, Part 1, we created those relative frequency distributions. And we did that by listing out all of the possible outcomes we could have, tallying up or finding the frequency, and then taking the frequency divided by the total. And that's exactly what we've done here, which is why it's called the relative frequency method. Okay, so we've actually already seen this, we just didn't put it in terms of a probability at the time. So now I'm trying to answer the question, what is the probability that we land on the space that is 8 spaces away? So the probability that I landed on an 8 based on my experiment was equal to 0.05, which is pretty different from what we found right up here with the classical method. The classical method said I had the probability of landing on 8 equal to 0.1389. From my experiment, I found that it was much smaller. Okay, now I'll be honest, I felt like I got really weird numbers when I was doing this, but I was rolling the die. There wasn't anything I could do to change it. So, okay, so again, just to recap, classical method, you are counting the total possible ways to get the outcomes and then looking at specifically, okay, now out of all of those outcomes, how many of those give me doubles or how many of those give me a sum of an 8? With this one, we were looking at actually performing the experiment, actually rolling the die, okay, to come up with these probabilities. So then with this, we have the law of large numbers. The law of large numbers states that as you repeat an experiment more and more times, the relative frequency probabilities get closer and closer to the classical probabilities. So what that means is if I were to repeat my experiment, and let's say instead of only doing 20 dice rolls, which is pretty small, I did 1,000. Okay, so I'm repeating my experiment 1,000 times. if I were to do that and come back and recalculate the probability that I rolled an 8, this number, this probability of an 8, would be much closer to the number that I had up here. It may not be exactly the same, but it would be pretty darn close. So that's what the law of large numbers says. As you repeat a probability experiment, actually rolling the die more and more times, that probability will get closer to what you would expect to see based on the classical probability. Okay, and then finally, I have an example here of 2 ways that you can interpret the probability of an event. So what I have here, this is a relative frequency probability. What we had was a group of 1,000 people, and we looked at what type of employment did they have. So we had a private company. There were 597 people who worked for a private company. So that probability was equal to 0.597. There were 141 federal government employees. 97 were self-employed. 92 worked for a nonprofit. 59 worked for a local government. 12 for a state government. And 2 had some other type of employment. So we looked at all of those, found the probability of each of them, added them all together. That gave us a probability of 1. So now we're going to look at the way to interpret these. So the first thing I could do, we're going to focus on the private company. The first way I could interpret the probability is to say that 59.7% of the employees in this group are employed by a private company. This is called the group interpretation because you're looking at specifically for this group of people. What percent of this group had that occupation? The second way I could interpret this is if I were to randomly select an individual from this group. So I have 1,000 people in front of me and I say, hey, you right there with the brown shirt. Okay, so I randomly picked one person. The probability that that person works for a private company is 59.7%. This is an individual interpretation. So I can take the probability by looking at the entire group, but then that probability also applies to the individual. So for example, for the federal government one, I could randomly pick one person, and the probability that that person works for the federal government is 14.1%. And this is still looking at just the 1,000 people that I have in front of me. Okay, so that's also going to be very important to remember is that the probability for a group also is the probability for the individual. Okay, so I hope that made sense. I hope this was a good introduction to probability. And that's it.